who will tell us about the status of the statistical Parton distribution. Thank you very much.
So, there is something there? No, I shall try to convince you after research which lasts more than 20 years, which is based on the idea of Feynman and other people. Feynman is the one who half century ago invented the Parton model to explain the scale invariance in deep inelastic, that the boundary condition for the Altarelli-Parisi equation should be expressed in terms of quantum statistic distribution and not with the polynomial that people use. So next. This, as I said, there was a proposal by Nikolaos Davis from Japan, Feynman and Field from the United States, that in the proton there is a symmetry in the C, so more V bar than U bar, because of the Pauli principle, because since in the proton there are two U and one V, it's easier to accommodate a V bar pair than UU pair. This idea has been confirmed by the defect in the Goffin some rule that says that really there are more V bar than U bar, and also by the study of the radium production in proton-proton and proton-neutron, which shows that the ratio V bar on U bar is an increasing function. In fact, before was not, because the stream is like that, and after a good measure is like that. So, I say, this, if you apply Pauli principle, means that you have to apply quantum statistics, because Pauli principle works for statistics. And so you have to use Fermi-Dirac distribution for the fermion, and Einstein boson, and also since the potential is zero, is Planck for the gluons, that I will show that are in very good agreement with the data. Also, there is an important thing that the Altarelli-Parisi equation are based on two elementary processes of QCD: the emission of a gluon by a quark and the transformation of a gluon in a cuckoo bar pair. What is the assumption? That for the non-perturbative regime before the perturbative regime of Altarelli-Parisi establishes, then you reach equilibrium. And so you apply statistics, and since the PDF are probabilities, to apply statistics to probabilities is not so bad. And the important thing of this equilibrium condition, that automatically you find that the bar is larger than the U bar, but also you predict delta bar positive and delta D bar negative, which has been confirmed by the Rick experiment with polarized proton in the production of W mesons. So, you know, when you have some idea that predicts things which after the prediction are in agreement with the experiment, you should somehow believe it. Then there was when we first wrote compared with the experiment, then we realized we could not write exact Fermi-Dirac function, but we used some ad hoc factors. But then, when you extend it to transverse degree of freedom, you account for this factor. So sometimes we will see somehow an such in the previous work, after was shown to be completely consistent by applying this.
Sorry. Sorry.
Thank you very much. Those words for this. Sorry. Bravo, eh? Thank you. Yes, yes. Then we extended recently to the production of the ampere, and we found also the distribution for the pion, which has a very high potential. And then there will be a conclusion. Next. You know, just something that you know very well, that QCD predicts the confinement at small the infrared level at small q square, but then it changes at high q square asymptotic freedom to understand the deep inelastic scattering. So the proton has a completely different aspect. When you have that q square equals 0, it's 3 quarks bound by color. Instead, when you go in the deep inelastic regime, it becomes a incoherent sobreposition of quarks, gluons, and antiquarks with probability, so completely different thing. But then, very important, other people before us try statistics, but they did not understand that the right variable to use for this, they use energy, because one is used that energy should be. Next. Instead, the reason then also normally they use the standard distribution with a polynomial a x b 1 x to c multiplied by polynomial. But this was completely empirical. There's no physical motivation. It's simply it's useful to simplify calculation, but there's nothing there. Next. Then one should say that the Parton distribution is not valid for any value. For you should have IQ square. Also, you should have that the mass square should larger than the mass of the resonance, because Parton model is a perturbative, and you cannot apply it when you create a resonance. So when you apply at the boundary condition, you should take a limited range of that. What I want to say is that there are beyond the fact that the bar is larger than the U bar, delta bar positive, delta D bar negative, all elements predicted by the statistical approach, there are other reasons to favor this statistical approach, property typically of quantum statistics. Next. In fact, I would say the role of this very long research is to show that the idea of the role of Fermi, of Pauli principle to understand, proposed by Feynman and others, brings to a precise formulation that at the boundary condition, this is a work in collaboration with the Social Society from Iranian Republic and Francesco Tramontano from Italian Republic, then at the boundary. So this is the right point to next. The other phenomenological facts which favor the statistical distribution is the fact that there is a correlation, because if you consider also the spin, there are in the proton, for instance, 4 up, down, the up, and the down. And we see a correlation typically as the one of the Fermi sphere, that the fact that the the valence partons, which higher first moments, so the more of them, are also broader distribution because they fill the first levels, and then there is this correlation. And this correlation happens for all the four partons for the parton. Next. Next. Oh, then there's an important quality which is taken by experiment, that at die X, when the X is larger than the higher potential, which happens to be for U up, the one which is more present in the proton is 0.46, then you have the common behavior Boltzmann, exponential minus X on bar X, where bar X is the temperature. Of course, is the dimension of the variable we have to use. In the figure I shall show at the end, I shall show how well this behavior, which happens for the fermions, happens also for the gluons at large X, showing the universality of the temperature. And so I would say a smoking gun for the statistical approach. Next. So what I said before, that then we shall write this distribution Fermi-Dirac for the fermions, Bose-Einstein, but which becomes Planck because the potential of the gluon for the equilibrium condition should be 0, and so we have no polarization for the gluon and Planck form for the gluon. Next. Oh, and then what I said before, people, when they come to think about statistics, just use the energy. But there is a reason why in statistical mechanics energy appears, because there is the constraint sum Ni epsilon I equal E. Instead, for the Parton, there is the constraint that they should carry the momentum of the proton. So instead of the energy should be X. So since normally, unfortunately, elementary particle physics do not do so well statistics, someone uses the energy instead to use X, which comes better. Next. Then there is some rule for the transverse energy, which is seems very tricky, because says that not only the momentum should carry, but also the transverse energy, which is the difference between the energy and the momentum, which of course is inversely proportional to the momentum. But then you multiply for the momentum and you write some rule with m squared at the right hand side, and this accounts for the factors we put in 2002 to fit the data, which seems somehow ad hoc, but now we can explain. Next. Then I said also in the beginning, then we said the bar larger than U bar X positive, bar X negative. Other people found this, but they just said we predicted that. And also there are, I said before, that you make the ratio of neutron to proton, F2 neutron to proton, delta U su U, delta D su D, and this, the first decreases, and the second increase regularly, are predicted by Fermi-Dirac. So you see, we found a lot of prediction, which normally people describe data adjusting the parameter. Instead, we simply predicted this behavior. Next. Then I have to be somehow unfair and speak of the disadvantage of the standard parameterization, because at ERA they had very good data, but they, to use this polynomial without any theoretical justification to describe the ratio D on U, they should put an ad hoc factor 1 plus 9.7 each square to have for the U, to have the decrease of D in the region of space that instead we simply describe with our approach. So they have to invent some factors a posteriori. No, we predict a priori. Next. Then this is the formula in which you have the formula dependence on X given by this Fermi-Dirac, and we have the Fermi-Dirac also for the transverse part. And then we have at the end, instead of the factor XQ polynomial which put arbitrarily, we have this factor that is completely justified, and is normal that if for a Parton xq is larger than the other, also epsilon q. But this is the right formula. Then the next term is Jaeger twist, which is not so much beyond the Parton model. Next. Next. Once that we had to include for data is a diffractive contribution that may be a shadow of the gluon which are there, gluon which go to the cuckoo bar, which gave at the time we studied that an increase in cross-section of small x. Now experimentally somehow changed the data, so it's not our fault. If we fix a parameter for the data defined, and after the change, it's not a problem of theory, it's a problem of experiment. But then, since they predict an infinite number of partons, to give no contribution to the famous quark model, quark number sum rule that in the proton human U bar is 2 valence U, Diemann's bar equal, and also the Bjorkin sum rule, we impose that this contribution is equal for U, D, bar, D bar, both helicity. Then this is more controversial because sometimes experimentally change that. Next. So I say the ad hoc factors we had introduced were explained by the extension. We can go further again. Next. So we have the form. It's very nice, the form for the gluon, because it's a constant x to bg, and then the exponential, the typical Planck form, exponential x to x bar, which plays the role of the temperature, like exclude the potential, -1. And then when at the end, if I have time, I will show the comparison with data, somehow unofficial, that I stole somehow, but I cannot say whom I stole, shows the perfect evolution from a power behavior as small x to an exponential at x with the same temperature of the fermion. And also for the anti-quark is the same reason. So somehow it's very solid. Next. I said that we have for the gluon the Planck form for the equilibrium condition, and also no polarization. There is with this some problem because my French collaborators thought to explain the polarization in the jet formation with the gluon But then you cannot have two-gluon polarization because to predict all the spin, isospin asymmetries in the proton which are shown, you should have delta G equals 0. Of course, the polarization is due to the quark and not to the gluons. Again, next. So I say that there is this equilibrium condition that say that the potential of the quark with given helicity is opposite of the Swiss antiparticle with the opposite helicity. And so for this reason, you think we have this property. For the disentanglement of quark-antiquark is helped by the quark number condition, but instead for the polarization, it just comes from this property. Next. Also, you know, I say that when we, I somehow repeat, when we compare with ERA, we found that due to their parameterization, we were in the agreement with ERA from 0 to 0.2. But then they, with this factor 1 and x2c, fall very rapidly. Instead, the Boltzmann formula is softer, and at the end, I will show that this is shown by data. Next. It's very important, the stability, because we compared our parameters as found in 2002 as in 2014. And you say that the parameters, the temper, 0.099, 0.102, so 3%. Potential of X just very near, all potential very similar. So a difference of other parameterization, it seems wrong, change completely. Our parameterization in 12 years did not change the parameter. So it's a proof that the parameterization is right. Next. Thank you very much. I should stay open. Next, because I was already saying. So I spoke that it is better that you can go on. Next. So in reality, the conclusion. What I already said, that while the standard parameterization gets the decreasing of the distribution just when you approach X, always X by 1, always more fast, we have this in this range, and then this is what happens. Next. Also, it was a nice result that since we fixed the parameters at IX from the measure in the region where the valence Parton dominate is very well measured. And so we found a very good agreement with the ratio between neutron to proton, D sub rho, 0.22. Which was also found by published work by Accardi, Melnichuk, and also another person. But I have to say that when I told to Accardi, he said, now we found 0. I congratulate for the stability of their predictions. Then next, let's see if I do it. Next, so I did at the conclusion. The goal distribution is by this Planck formula that I will show it at the end. Next, next, because I have to go to the conclusion because it's not conclusion. Let's say I read the agreement of the Fermi distribution found in 2002. Inspired by quantum statistics, and the one found by ERA is an important confirm of the validity of the statistical approach, which say at the beginning has been motivated by the idea of two Japanese and two Americans, the Pauli principle implies isospin symmetry in the sea. The theory has been proved by extension to transverse momentum, and also is precisely explained because it says this is the boundary condition to the Graph-Waltarelli-Parisian equation. So the agreement with the value. Also, we predict this exponential for an integrated PT distribution. Next. See the decrease of the valence distribution is well described in the range of the smaller the up, a larger potential. Next. So I insist, the interesting property that large X, where the measure are difficult, then we predict what happens to large X from parameters fixed in the region whether you have a very good measurement. So we have not the ambiguity. A large X, generally the other people show big uncertainty, not again I spoke more of the spin symmetries. Next. Then the gluons I will show how well are described by us. And also the last thing that we applied also to the pion, and then we found with the larger potential with the pion, which explains why pion on antiproton dominates the production of the ampere. And then we can put the figures. The first fit PDF. You see how well is described. Power, small x, and after evolving the potential. I was really impressed by the agreement, and so also with the parameters were very near to the ones found in 2002. So, you know, 2002, you predict something, then you modify very slightly the parameters, and you find the disagreement. Then let's put B1 and B2. Then is what we found for the production of the ampere for the pions, which for pi minus you have very important contribution for the valence U bar, which is very present, the valence U bar, and the valence of the target. Also B2 for completeness. And then JPC pour tutti di bar sul bar, so I finish JPC. Let's see, JPC, let's see. You see, before there was the blue. Instead we predict always the, and then there was our curve is the red, and then you see how well with the new points. The old points with big mistakes, and then the new result. Many people should say, I'm wrong because it's this. We say, no, we are right because the experiment has been done better, is like that. I thank you for the attention.
Thank you very much. Are there questions? From the audience here or online? I don't know if there is. Yes.
Maybe I've lost some parts of the talk, but in any case, is it possible? So you have new initial conditions, right, for your PDFs, correct?
Sure.
And is it possible to embed this condition into an evolution program in order to do?
You see, my problem is not to compute the evolution, because Altarelli and Parisi, my fellow of the thesis Altarelli, more than 50 years ago, did. So I say, boundary condition, they do not know. So I complete, you know.
Yeah, but is it possible?
I complete. So when you know at 4, at 4,
Sure.
if it's good at 4, then if evolution should predict the right one.
No, I'm not questioning that. I'm saying if we, because there are programs which are available. I mean, usually all these groups that generate Parton distributions, they just give you the evolved result. They don't give you the codes, right? And so there are codes actually which are available. For instance, I wrote one which goes to next to reading, so it's very precise, which I have never used, where you can enter and plug your PDFs, your original initial conditions, and then compare with the evolution of others. This is possible to do.
You see, the problem is this, that the evolution requires a very complicated CD, and it's done by people like you that study that. But then it's important the starting point.
Absolutely.
Because if you started from a starting point which is wrong, then the evolution is not. So when I remark all the contradiction, I didn't say all the one by the era using this, this is stupid polynomial formula, then they had a mistake from the beginning. So somehow I also asked, you do the evolution, but start from that. But people which work in that feel so stupid to have not taught to them these very simple things that have a very hostile attitude. They do not want. But of course, as I show you, there are many phenomenological facts predicted that should convince that it's better to look to the. Then, luckily, recently, some people which works on that contacted. But of course, there is all the subroutine already done. People do not want to check.
That's right.
The first person which will use this will be very, very famous.
Okay, very good. Okay, thank you.
Thank you. Are there any other questions?
I have to be near because I have to see them out to understand.
Okay. I'm asking if there's any other question from the audience here. No, I don't see, and online either. Oh, no. Okay, then thank you very much again for the nice talk.
I'm sure you are, you know that there will be a reception today, but you are required to sign up the sheet which is at the registration desk during lunchtime.
Thank you. So now we continue. The next talk is by Paul Frampton. And we are very pleased to have him talking about additional baryons and mesons.
Oh, there.
Very good. Thank you. The floor is yours. Please.
Thank you.
Okay, well, first I want to thank the organizers, especially George Zipanis, for inviting. Is it switched on? Hello, can you hear me now? Okay, So I want to thank the organizers, particularly George Zupanis, for the invitation. And it's very appropriate this is in the QCD section, because I think I've only ever written 2 papers on QCD in my career, almost 500 papers. And this is the second one. The first one would be Carlo color, I suppose. But this, what I'm talking about in this presentation turns out to be correct. And for the moment, it is a speculation. It will mean that there's a very promising future for QCD and the quark model for the 2020s and the 2030s, because I'm going to speculatively predict that there are a huge number of additional baryons and mesons at energies which can be reached probably only with the FCC. Although the key signature that this is correct is accessible to the LHC, and in fact, as Albert Dweck briefly mentioned in his talk, the key signal is to find the bioelectron, which is a doubly charged resonance in like sign leptons. And okay, as it says, I'm affiliated with the University of Salento, and I live in Oxford, UK. Now, the original paper is a very long time ago, well over 20 years ago, and I must admit that when I wrote that paper, I thought the probability of it agreeing with the experiment was less than 1% at best. But as things evolve, I would give it a much higher probability now, maybe even as high as 80% or something like that. One reason is that when I wrote that paper in 1992, I expected there to be many alternative models would appear in the next few years, but actually 29 years later, there isn't really any alternative model to the original one, and that makes it more likely. And very recently, my colleague Shelley Glashow has become very interested in it, and that gives me more confidence as well. And these papers here are written with Italian colleagues. Red button, it's not red, including Claudio Coriano, who is here, and 2017, 2018, and the third in the series is being submitted, hopefully to be accepted. I don't know. And then the present talk is based on this paper, which has just appeared on the archive, and it's published here. So this is what could be regarded as the most likely first beyond the standard model particle, and it is being searched for both at ATLAS and CMS, according to what I hear from CERN. And the key model, the model can be called the Bioelectron Model. Originally, I called it the 331 model, but that has caused confusion because it's not enough to have the gauge group SU3 cross SU3 cross U1 as a generalization of SU3 cross SU2 cross U1, but it also has to have particular assignments for the fermions and the charge operator and so on. Now, I don't have time in this talk to explain the background of this. I think I've talked about it before in this conference. But in making an extension of the standard model, there are infinite number of possibilities, but one would like it to be motivated by answering a question which is within the standard model and testable by explicit predictions. The Bioelectron Model has two things in its favor. One is that it explains the existence of three families, which is one of the biggest mysteries in the standard model. And it explains that by a particular way of canceling the triangle anomalies, which fixes the various fermion and gauge bosons. And it is testable Equally important, perhaps more important than the explanation of three families, is that this particular model from 1992 has the property that the new physics must be at a few TeV. It cannot be pushed up to arbitrarily high level. For a reason I don't have time to explain, but that's a peculiarity of this model, which means that the new physics should be accessible to the LHC, at least some of it, but what I'm going to talk about will inevitably require more energy from the LHC, for example, in an FCC. So this gives at least a scientific motivation for building an FCC if the LHC finds evidence for the 331 model. Let me just very briefly run over the 331 model. So it simply generalizes the normal SU2 to SU3, and it changes the significance of this U1. The charge operator is embedded like this with suitable normalizations. And so when there is a triplet, the quarks therefore must be in triplets or anti-triplets of this SU3, and the charges in a triplet are x plus 1, x minus 1. So notice that x is the electric charge of the middle component of a triplet or anti-triplet. So the way the standard model particles are put in is that the leptons, there are no additional leptons, and each family treats the three left-handed leptons to be in an anti-triplet of SU3. And because the middle member is a neutrino, they all, with no charge, they all have x equals 0. In the first family, since it is a triplet, we must put in an extra quark, which is going to be the central point of this talk. So there is a quark in the first family, capital D with charge minus 4/3. There is in the second family, a capital S with charge minus 4/3. And the x values are easy to work out. Now, one crucial point is that the third family is different, cannot be the same. And the third family has bottom, top, and a T quark, which has charge. No, go ahead. Is this a question? No. Charge. Well, the audience can go on Zoom and read it more easily, perhaps. They can look on the laptop. So you can't read any of it. Well, if I say everything, then you can hear. And the extra quark here has charge plus 5/3. And the x values are easy to work out. And so what will be the first particle to be discovered? Well, it actually isn't these three extra quarks. The crucial particle is, so as well as these extra quarks, we have 5 extra gauge bosons, because SU3 has 5 more generators than SU2. One of them is a Z prime, which is not terribly interesting because it's very, very broad with a width comparable to its mass. But the other 4 are called bileptons, and they are either doubly charged or singly charged. The singly charged are harder to find because they decay into neutrinos, but the ones that are easy, as a theorist I can say easy, but unquestionably it's difficult for the CMS and Atlas, but possible, I am told. These bosons have lepton number 2, and they decay into same-sign leptons. The best mass estimate I made with Coriano, 1.29 TeV. This mass estimate is not sharp, but that's roughly where it should be. Let's say 1300 GeV. And so this is being looked, this particular particle is being searched for at CERN as we speak. And as an optimist, I hope it will be discovered in 2021. Then everything I'm going to say after this will be a sharp prediction. At the moment, it's a speculation. So let's take this model for the moment as correct so that I can go on. Then physics for the next 10 or 20 years becomes very exciting because you have a whole panoply of additional hadrons unsuspected by anybody until today, unless you've been reading my papers. So these extra quarks have these peculiar charges, and of course QCD will bind them into baryons and mesons. They will bind with the light quarks and with each other. And so let's briefly, for the next 15 minutes, discuss these baryons and mesons. Let's suppose these new quarks have a hierarchy of mass T bigger than S bigger than D by comparison with the light quarks. And as I mentioned, one very important point of this model is that these quarks cannot be arbitrarily heavy. They must be below a magic scale of about 4 TeV, 4.1 TeV, because this is a reason I don't have time to explain in detail, but it's all to do with embedding SU2 cross U1 and SU3 cross U1, which is possible only if the energy is below this, because above this, it will violate unitarity, because one of the couplings will become imaginary. That's very unusual in model building. Within almost every model I've ever built, the scale can, like in supersymmetry, for example, the scale can go up arbitrarily high. This one cannot. So let's just take a look at the mesons and baryons. I'm going to exhibit only half of them, and the charge conjugates go without saying. Oh dear. Can anyone see that? Well, let me just indicate what it is. So, oh, good. Yeah, if you keep doing that, that will help a lot. So let's take a heavy quark with a light quark, large antiquark. So this is a meson. Now, one peculiar thing, one of the several peculiar things, is that these heavy quarks are, as usual, they're color triplets with spin a half and so on, but they carry lepton number, which is a new property of this model. And this means that these new mesons carry lepton number. In this case, either +2 or -2. And of course, they have these multiple charges. So the charges of the mesons are -2, -1, +1, +2. There should be something on there, up higher up. No, yes, good, perfect. So now let's look at mesons made of heavy quark, heavy antiquark. And again, the charges in this case are either -3 or neutral, and the lepton numbers are either 0 or +4 once we involve the capital T. Okay. Next, we think of a baryon which has a heavy quark and 2 light quarks. Then these have electric charge allowed to be even higher, -2, -1, 0, +1, +2, +3, and they start, the lepton numbers are either +2 or -2. It's quite fascinating. And then the next table, the final two tables along these lines are baryons. I'm sorry, there should be, there's a typo there. There should be a small q here. So it's 2 heavy quarks and 1 light quark. In this case, the electric charges run from -2, 3 to +4, and the lepton number increases to +4 or -4. And finally, if we have a baryon, now this might be quite heavy, but if we have 3 TeV quarks, making a baryon, then the electric charges range from -4 to +5, and the lepton numbers range from +6 to -6. Now, these very high lepton numbers make these baryons and mesons somewhat quite different in an interesting way, because their decay modes, which the rest of the talk I talk about a few decay modes, will involve quite a lot of leptons, because lepton number is conserved. So let's assume that the masses follow this inequality. And so we have a certain hierarchy of possible masses. So the lightest of the TeV baryons and mesons are those containing just one capital D quark or one capital D antiquark. And the next heaviest contain one S quark or one S antiquark, and so on. Now, the decays of these heavy quarks are typically into a light quark plus a bilepton. For example, D into usual D plus Y minus. And that Y minus, the predominant decay mode of the bileptons, is into 2 leptons with lepton number 2. So you have, for example, electron plus anti-electron neutrino, not anti-electron neutrino, and so on and so forth. And so if we go to the hadronic scale, hadronic language, then this particular meson, this would be one of the lightest new mesons, will decay into a pi minus and 2 leptons in one of the 3 families. And there are variants, there are flavor of variants. And we can replace, for example, the D up here with, of course, it can decay into a U and Y minus minus and so on. Yes, that's what I just said. So D, capital D into U plus Y minus minus, and the Y minus minus, this is the thing they're looking for at the LHC, is the Y minus minus will go into 2 like sign leptons. At LHC, probably, or almost certainly, the easiest one to see is mu minus plus mu minus. Maybe I should say that electron-electron scattering has never been looked at above about 1.1 GeV. It's been considered at various colliders, but now there is the opportunity, after no structure at all, this sort of empty channel, as it's usually thought, suddenly at 1.3 TeV, it's expected to have a resonance. Similarly, at the hadronic scale, it will decay into a pion and 2 like sign leptons. This is just continuing the same chain of thought. So again, for a meson like this one, DD bar, it will go into a pi 0 and 2 leptons. And again, it's sort of obvious how to replace the flavors with the other flavors. And similarly, DD bar can also go into pi plus and like sign leptons again. I'm going to get going. Then we can look at the baryons, and for example, this is one of the lightest baryons. It can gain a proton and 2 leptons. There are other possibilities where it goes into an N star double plus and a bilepton, which goes into like sign leptons. Now, the thing that happens if you proceed to more complicated, like the heaviest baryons, I won't bore you with all these intermediate possibilities, but once you get to the heaviest baryons, they then have these cascade decays into lots of leptons, I'm just illustrating, once you have a capital S, it can decay either into D plus Y minus, or this can decay into capital D plus Z prime, the new Z prime. And then you have a cascade of the Z prime and of the D. So you get lots of leptons. And similarly, capital S has similar decays. It's quite fun to work these things out, since as far as I know, they've never been worked out before. But I'm assuming a certain mass hierarchy. As I said, that T is heavier than S is heavier than D, which sounds plausible. And eventually, once you start looking at baryons with S in it, it can decay like that. SUU can decay into N++ plus a bilepton. Of course, it would be interesting to use QCD to try to figure out the properties of these heavy baryons and heavy mesons. And here is another baryon decay into a neutron and like sign leptons. Now, you know, obviously, if one knew the masses of these quarks, it would be justified to look in more detail at how these decays happen and to use QCD and so on to analyze it, which hopefully next year we might have a whole talk about that if the experiment cooperates. And it's premature to do that now, but I've just given you sort of a broad idea of how particle theory might evolve in the 2020s, at least. And you get more and more leptons. Let's see. Now, what about the masses of these things? And what about the LHC with its 14 TeV? Not even 14.1. Anyway, it doesn't matter, because these things are seriously heavy. It is reasonable to expect. So, for example, they are bounded, each quark is bounded by this special number, 4.1 TeV. And so you could say, how heavy is this capital T quark? Of course, we have no idea, but it's certain that it's less than 4 TeV, but it could be as much as 3 TeV, say, in which case this TTT baryon might have a mass of, I'm coming to it, might have a mass of 9 TeV. And you have to pair produce them because of lepton number. So 18 TeV is bigger than 14 TeV, forgetting the fact that the quarks only have 1/6 of the energy. But if you have a future circular collider with 100 TeV, then it will be fantastic, because then you can pair produce these things. And these have, I mean, I didn't even finish in my notes. I tried to figure out all the decays of this thing, of which there are a huge number of channels. The simplest one I could find for TTT is proton plus 4 positrons plus 2 anti-electron neutrinos. And you see this indeed has lepton number -6. This is the simplest decay of this baryon, but there are amazingly many complicated possibilities. So now I should emphasize that all these tables are purely speculative, and you can forget them immediately unless the LHC finds, the easiest thing to discover seems to be the bilepton, which is the doubly charged gauge boson in like sign leptons. We have our fingers crossed that that will show up in 2021. I'm an irrational optimist, But there's at least one other particle theorist who seems to think that might be true. And then once that happens, all these 5 tables will become a sharp prediction. These things will have to exist. And our experimental friends will have to find them, and build an FCC and find them with that. I hope to be alive when the FCC finds them. What's as soon as the FCC could run? 20 years? 2060? Well, I'll only be 117. 2060, I'll be 117 years old. It's a question for biology more than physics. Can't you speed it up a little bit? Anyway, that's, thank you for your attention.
Thank you very much for the nice and optimistic talk. Do we have questions? Yes.
Franco.
Theory from what you say, like from SU3, SU1 to SU5, SU10, there are some unifying case theory that you can introduce in your talk, in your approach.
Okay, thank you. That's a very good question. And I will answer it with a good answer if you give me the microphone. Oh, I do. Yeah. Now, Franco is asking a very good question, is how to make a grand unified theory which contains the 331 model. Now, funnily enough, earlier this year, maybe January 2021, I had a long discussion with Shelley Glashow about SU5 and why did SU5 fail, for which there are many reasons. Now, if this is all correct, the 3 families are different. They're absolutely different already at a TeV scale. There are the first 2 families, and then there's the 3rd family, and the 3rd family is definitely departing from the first 2 families, as you can see by the quark structure. Now, this means that any grand unified theory of the old-fashioned type of SU5, O10, E6 cannot possibly work, because what our colleagues Georgia and Glashow did in 1974, they put 3 10+5 bars on the assumption that they would remain sequential up to the gut scale. Now, in this picture, that doesn't happen. So there can't be a grand unified theory of that type. And the answer to your question is that I don't know how to grand unify this. I have tried and have thought about it, but for sure, well, we have some very speculative, we don't really have any good idea. And but the point is, it can't be of the old-fashioned type, you understand? So it has to be something really clever, which you can think of in the next year, how to put this into a bigger group. There's no obvious way. But that's a very important question, yeah.
Thank you very much. Do we have more questions? Yes.
I might have missed that, but was there any initial clue that made you use the lepton triplets, or you just use lepton triplets to see what lies beyond?
I'm sorry, I missed the first sentence. Why I used what? Triplets of SU3?
Yeah, the SU3 leptons. Was there any clue that made you introduce these triplets, or it was you just used these triplets in order to see what lies beyond?
Well, the point is this extension from, let's call it 321 to 331 makes it essential to put the quarks in triplets. So there's no way of avoiding one extra quark per family. That goes with the SU3. The other, I guess the reason for introducing the SU3 originally was to study the triangle anomalies very carefully with 3 families, and then the realization that, well, the first realization is that to necessitate 3 families, it's essential that the families have different anomalies, otherwise they won't cancel between each other, if you see what I mean. So it's essential that each family does have an anomaly, and then the 3 families together can be proportional to, say, 1, 1 minus 2, as they are here. So you need, it needs the extra gauge group so the triangle anomalies cancel between the inter-family cancellation, right? That's the original reason. Then the extra quarks are forced upon you, and all the quantum numbers are fixed, by the way. The charges and the lepton numbers and so on are all definitely assigned by the structure. I'm not sure if that answers your question.
Oh, it answers clearly. Thank you. Thank you.
Oh, okay.
Thank you. Do we have more questions from the audience here or online? No, okay. Then thank you very much again for the very nice talk.
Thank you. Thank you for your question. Very good question. I've been thinking about it. We can discuss.
And now we move to the
Oh, good point.
last talk of this morning. Very good. So the next talk is about intermittency, analysis in heavy ion collisions, a review of the current status and challenges by Nikolaos Davis. So we can see your slides. Please, you can start.
Thank you. I would like to thank the organizers for inviting me to talk. I will give a review of intermittency analysis in heavy ion collisions, its current status and the challenges we face. So I start with a picture familiar to many of you, the phase diagram of strongly interactive matter in terms of temperature and biochemical potential. So as we transition from hadronic matter to quark gluon plasma, at low biochemical potential and high temperature, we have, as we know from lattice QCD, a smooth crossover transition. Whereas at high biochemical potential and low temperature, we have a first order transition line, as we know from effective models. So it's quite reasonable to suppose that this first order transition line ends at the critical point, where a second order phase transition takes place. This critical point is of physical importance because the system there becomes scale invariant and can be described by universality theory. And collective modes play a large role. And all of this gives a very good physics signatures. It gives very good physics signatures for the detection of the critical point. The detection of the critical point is the main goal of many heavy ion collision experiments, in particular the SVS N61 sign experiment. And in order to detect the critical point, we have to look for observables tailored to it and scan the phase diagram by varying the energy and size of the collision system. Observables suitable for the critical point can be divided into 2 large categories. On the one hand, we can have event-by-event global fluctuations such as variance, skewness, and kurtosis, where we expect to see a non-monotonic behavior as we approach the critical point. On the other hand, as is the case for intermittency analysis, we can look for local density fluctuations of an order parameter, which forms a stochastic fractal in transverse space. The order parameter is defined as a quantity that takes a zero value in the disordered phase, the quark-gluon plasma, and a non-zero value in the ordered phase of hadrons. And options for the order parameter can be either the chiral condensate, the sigma quark antiquark condensate, and also in a finite density medium, the chiral condensate couples to the net baryon density, and it uses critical fluctuations. So the net baryon density is an equivalent order parameter. We can use it to detect the critical point. As I mentioned, in the vicinity of the critical point, the correlation length, the characteristic length of the physics of the system diverges to infinity or to the full system size. And therefore, the system can be described by the universality class to which it belongs and the dimensionality of space with an effective theory. And this determines the critical exponents, which are the power laws for which various thermodynamic quantities follow, the divergent part of various thermodynamic quantities follow, which in turn dictate correlations, the form that correlations take, correlations of fields take in the configuration space. Performing a Fourier transform, we can obtain the corresponding correlations for fields in momentum space. And in the case of an infinite system that falls within the 3D Ising universality class, we have the following predictions for the form of correlations of the sigma field and the two particle correlations in the net baryon density as a function of transverse momentum transfer. Now, experimentally, in order to detect critical fluctuations, we turn to the phenomenon of intermittency. This is the equivalent in heavy ion collisions to the optical phenomenon of critical opalescence, where a liquid approaching the critical temperature has density fluctuations larger and larger in size, and when they become comparable in size to the size of the system, then the scattered the light of large wavelengths scatters and gives it a clouded appearance. In particle collisions, the equivalent is a singularity in the limit of vanishing momentum transfer. So we can probe the transfer momentum of particles, and we can make two additional approximations. We can use the net proton density as a proxy for the net baryon density, as it carries the same critical fluctuations. And furthermore, we can drop antiprotons and study only the fluctuations of the proton density, as the antiproton number is negligible in the systems we study. In order to perform intermittency analysis, we use the tool of factorial moments. We study the scaling of factorial moments. This is a technique pioneered by Bialas and others as a method to detect non-trivial dynamical fluctuations in high-energy collisions. And it works as follows. We partition transverse momentum space into a number of equal size cells. And then we calculate this quantity, the second scale factorial moment, essentially the scale number of pairs of particles per cell, as a function of the cell size, or equivalently as a function of the number of cells. Now, of course, for an ideal critical system, this would suffice, the scaling of F2. But in an experiment, we of course have a background of non-critical pairs that have to be subtracted in order to get to detect intermittent behavior. So we follow the following scheme. We can partition the total number of pairs into critical pairs, background pairs, and plus a cross term. And rearranging and scaling this, we can define a correlator, delta F2, in terms of the moments of the original data, the moments of the background, and this ratio, which is the ratio of the particle multiplicity of the background particle multiplicity per bin to the total multiplicity of the data. Now, this scheme is complicated by the cross term, but through critical Monte Carlo simulations, there is evidence that we can simplify this in the limit of dominant background, so where the background is approximately equal to 1, which is the case for virtually every experimental system we have studied so far. And then we can approximate the correlator by simply subtracting the moments of the mixed events from the moments of the data, and detect intermittency present in the correlator as a parallel scaling in the limit of large M values, small binnings. We have the following theoretical prediction for the intermittency index in the case of proton density. Now coming to experimental analysis, the first application of intermittency analysis was in Na49 carbon-carbon, silicon-silicon, and lead-lead systems at the maximum SPS collision energy. And we studied the intermittency in dipyons, so pi plus pi minus pairs, which reconstruct the sigma condensate. And on the left, you can see the results for the correlator delta F2, carbon-carbon, silicon-silicon, and lead-lead. On the right, the fitted values for the intermittency index for each of the systems, except for lead, which is not well defined, compared to the critical prediction for the sigma field. Notice that we see intermittent behavior with an index of about 0.35 for the silicon-silicon system, whereas no such power law behavior is observed in the other systems at the same energy. Now, working with dipyons is complicated by combinatorics, so we have to work at the production threshold of the dipyons, and this is difficult. So in the next stage, we focused on the baryon and the proton density, and we analyzed proton factorial moments initially in the same systems. So here on the left plot, you see the factorial moments for the silicon-silicon system of factorial moments of protons for the original data in black, and the mixed events in red. And on the right, the subtraction and the correlator delta F2. The errors of F2 and delta F2 are estimated using the bootstrap method, of which I will talk in more detail later. And if we fit in the range of large M squared with a power law, with this power law model, we get this measurement, this value 0.96 with large statistical and systematic uncertainties. So there is an evidence for intermittency in silicon-silicon system. However, the uncertainties are considerably large. Now, this initial result motivated us to continue intermittency analysis within the framework of the SIGN experiment, which is the continuation of Na49 experiment. And there, two main systems were candidate for analysis: beryllium-beryllium and argon-scandium at the maximum energy. In the case of beryllium-beryllium, again showing the factorial moments and the correlator delta F2, we see that the moments of data and mixed events overlap, and therefore the subtractive moments fluctuate around 0, and no intermittency effect is observed in beryllium. Next, moving to the argon-scandium system, the closest in size to the silicon-silicon system so far. A first indication of intermittency in mid-central argon-scandium collisions was presented at CPOT 2018, in fact, within the Corfu Summer Institute. In 2019, we extended our set. We analyzed an extended event statistic set. And In this case, we performed a scan in centrality in the 0 to 20% most central collisions in 5 and 10% intervals, as well as the total interval. And we did this because centrality may influence the system's freeze-out temperature. So it has physical significance. Event statistics were moderate. We had of the order of 400,000 events per 10% centrality interval. Again, we calculated bootstrap confidence intervals for delta F2. And importantly, due to correlations within different bin sizes, between different bin sizes, it is challenging to determine confidence intervals for the intermittency index. Various approaches to this problem are being investigated, such as model weighting. I will give you details later on. But the algorithm scanning system so far is inconclusive. So in these plots, we first look at the 5%, at the results for the moments for the 5% centrality intervals. And these color bands represent roughly 1, 2, and 3 sigma intervals, confidence intervals for the correlator delta F2 for the given bin size. We notice that no signal seems to be observed in the 0 to 5 and 5 to 10%, so the most central collisions. In the 10 to 15 and 15 to 20%, we see some weak indication of scaling, but with very large uncertainties. If we go to 10% intervals by aggregating previous sets, we reduce the uncertainties of the correlator, but we lose resolution in centrality. Still, centrality dependence is evident. We see no signal in 0 to 10% and some weak indication in 10 to 20%. And also a very weak indication remains, a very weak scaling behavior remains in the 0 to 20%, much weakened. So given these results, we want to understand how the critical component behaves and how different critical components give rise to the behavior we see. And the way to do this is with critical Monte Carlo simulations. We use mainly a modification of the CMC critical Monte Carlo algorithm, which can be found in this publication, adapted for the case of protons. In this model, only protons are produced, only proton particles. One cluster of such particles per event, which is produced by random Levy walk with the appropriate fractal dimension plugged in. And this is a truncated, since this is a truncated walk, the lower and upper bounds of the momentum step of the walk are plugged in as parameters to the model. Cluster centers are exponential in transverse momentum, and their slope, the slope of this distribution is adjusted by a pseudo-critical temperature parameter. And lastly, the proton multiplicity per event follows a Poissonian distribution. So in this table, you can see a summary of the input parameters to the model. Now, if we take this critical Monte Carlo and we dilute it with random, replacing critical protons with random background protons, then we can build essentially an adjustable model for the moments of different at different background levels, different critical components. And you see here a simulation applied to a beryllium-like system. This line represents the moments of the pure system, pure critical system. And then we have larger and larger, we introduce larger and larger background. And notice that whereas the moments, the correlator falls by orders of magnitude in absolute values, the scaling persists for pretty high values, over 99% of background. So we can retain the critical behavior up to very high background levels in the delta F2. And by performing such a scan, our preliminary analysis shows that if there is a critical component in beryllium, then to obtain something comparable to the level of moments in the experiment, we have to have a 3 per mil at most critical protons component. This is important because, first of all, it shows that the approximation of dominant background is reasonable in the systems we study. Correspondingly, if we go to a simulation of argon-scandium system, we find again that we retain critical behavior up to a limit of about 5 per mil critical protons, rather down to a limit. So, as is evident by now, as should be evident by now, there are considerable challenges in pursuing a proton intermittency analysis, and let me spell them out. Particle species, and especially protons, cannot be perfectly identified experimentally. The candidates will always contain a small percentage of impurities. Experimental momentum resolution sets a limit to how small a bin size or large bins M we can probe. We need to work with a finite and rather small at that number of usable events. And then we have to extract the infinite statistics behavior, because this is we are looking for a statistical property. So we have to extract the infinite statistics limit from such limited data sets. And the proton multiplicity for medium-sized systems is low. Typically, we have 2 to 3 protons per event in the window of analysis, and 2 is the absolute minimum because remember, we're looking for pair correlations. And the demand to have high proton purity lowers it still more, because we have to throw away many candidate protons. And last but not least, the M bins are correlated. So the fluctuations of the M bins are correlated because the same events are used to calculate all bin sizes. And this biases the fits for the intermittency index and makes confidence interval estimation hard. The first tool that we can use to quantify uncertainties is the well-known statistical tool of the bootstrap, of the statistical bootstrap. This consists in taking random samples of events with replacement from the original set of events. So we take the original set and we draw with repetition an equal number of events as the one it contains. This constitutes a bootstrap sample, and then we produce of the order of 1,000 such samples of the same number of events as the original sample. And we take them and we calculate each of the statistics we're interested in, the correlator, the intermittency index, and we calculate it for each of the bootstrap samples exactly in the way as for the original. The implementation is very simple.
Sorry, you have 5 minutes.
Thank you. Then the variance of the values, of the resulting values of bootstrap samples, gives us an idea, an estimate of the standard error of the statistic. And in fact, we can calculate any kind of statistical distribution or confidence intervals, anything. So one application of the bootstrap is to use it to make correlated fits. And we do this by calculating from the data not only the phi2 and delta F2 values, but also a whole correlation matrix between bins. So we can use this estimated correlation matrix to perform a correlated fit, defining a correlated chi-square quantity. And you can see this applied for argon-scandium system. On the left, we have a correlated fit, the best fit with correlated correlation matrix, and on the right, an uncorrelated fit. I don't know if it's visible, but in the correlated fit, notice that the best fit line is estimated to pass below all the points, which is paradoxical, but is to be expected as the points fluctuate together. So they're either above or below the true values. This makes correlated fits rather difficult to work with and controversial. Also, replication of events means that bootstrap sets are not independent of the original. So we may get an idea with a bootstrap of magnitude of variance and covariance estimates, but we cannot trust the values themselves that we get. The central values will be biased to the original sample, whatever we got by luck. And correlated fits are in fact have been known for some time to be unstable. So we need a better approach. And this better approach is essentially to avoid fitting and use model weighting. And in fact, you will hear tomorrow in the talk by Fotis Diakonos in much more detail about this scheme. For now, I just briefly introduce the AMIAS algorithm, the model independent analysis scheme, which can be used to extract model parameter distributions such as phi2 from sets of data. And it works by sampling parameter space at random, then weighting the selected models by goodness of fit function to the data set. And here you can see essentially AMIAS estimating the intermittency index phi2 using the Parallel model for the sine experimental data, and we get well-defined distributions. Finally, the AMIAS, we can test AMIAS with a critical Monte Carlo, and what we can do is we produce 400 independent samples of argon-scandium-like moments. And then we plot the distribution here, and the black points represent one of these samples. So it's a typical sample falling somewhere near the mean trend. And then we can fit these models. We test millions of possible solutions, millions of possible intermittency index values on these samples, and we get an average chi-square. We can use it to estimate the distribution of the intermittency index, and we get a value very close to the plugged-in critical value to the system. So we can extract, in the case of the critical Monte Carlo, we can extract from a large number of samples the critical behavior we put in, despite the noise. And this should also work with bootstrap samples, although they are not independent. So we have a method of handling the system, correlated bins with AMIAS. Finally, there's a question of the statistical significance of the signal. That is whether random fluctuations could give us a stronger signal. And we have made a study of the statistical significance by comparing the moments, the distribution of experimental moments, the correlated delta F2, with random background protons. Here we show the experimental points overlaid. Notice that about 85 to 95% of delta F2 values, experimental values, are above zero in argon-scandium, above the zero line, and about 85 to 95% of random background values are below argon-scandium average. So we can estimate very tentatively a 5 to 15% chance of random background producing a spurious effect, which is not very large, but not insignificant either. So to conclude, intermittency analysis of proton density is a promising strategy for detecting critical point. However, this analysis is challenging in the context of an actual heavy ion collision experiment, always constrained in terms of available statistics, particle multiplicity, and proton identification. We have developed new techniques to better determine the correlator and intermittency index uncertainties, such as bootstrap errors and AMIAS weighting. Certainly, detailed exploration of refined models with critical and non-critical components is needed in order to assess experimental data. Analysis of different systems and collision energies is ongoing, such as lead-lead currently. Thank you.
Thank you very much. Do we have questions?
Did you try to analyze the ALICE data for this intermittency effect? So,
no, because if I'm not mistaken, ALICE data is not in the, so that the freeze out is very far from the expected location of the critical point. We need moderate energies, SPS energies.
I also have a question. What is the experimental prospect for intermittency for silicium-silicium?
Sorry, could you repeat?
What is the prospect for intermittency in silicium-silicium? Experimental prospect.
For the experiment, currently,
Very large.
you mean for a new data set of silicon? Hello?
Yes, we can hear you.
You mean what is the prospect for a new analysis of silicon?
Yes.
As far as I know, currently, unfortunately, there is no plan to revisit silicon. In fact, I believe it is a very good idea to go back, but currently there are no plans. So we don't expect new data soon.
Okay, thank you. Do we have any other question from the audience here or online? If not, thank you very much to the speaker and all the speakers of this morning. And now I guess we have some announcements.
Well, Carlo. So one point is that we would like that you